Hello, hello. Oh, there goes. Oh, hold on. Hello, Ash. Oh, nice. All right, wait. Hello, good afternoon. Oh, and even a wave. Whoa, I'm getting a physical wave from a physical person. Hello, Eugene. That's awesome. Okay. And hello, good afternoon, Sylvie. Thank you so much. Wait, someone else is here. See, this is the most. Do you issue me the personal challenge? Do you think I could actually spend 2.5 hours just doing this hello routine? All right, no, sorry. So good afternoon, Sylvie. Hello, Ashley. Hello, Marina. Hello.
Hello.
Oh, I even got all right. Hello. Woo! I mean, hello, Abigail. What people are coming, but definitely hello, Eugene. Also, let's just really. She's. Good afternoon, Giselle. Good afternoon, Ariana. Sorry, I went out of word. Oh, hello, Abigail. Oh, it's coming. This is like let the group therapy begin for me. I mean, you guys need therapy. Not that there's anything wrong with needing therapy. Good afternoon, Fatima. All right, we're here, and I missed out, and there goes my board again, of course. Hold on. Okay. Oh, good afternoon, Salady. Um, okay, okay. 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 It has been a long time since we rocked and rolled. I apologize. Thank you for understanding last week. And I thank you for understanding and communicating your confirmation so quickly to me. That meant a lot. Like that was a super annoying situation. I did not want to miss this class. We'll try to make up for time today. But for whatever it's worth, I always do that thing of giving points just to get confirmation because whatever, the communication just is helpful to both of us and all that. And I have to say, I think, and even though I took a while to get back confirmation of receiving your confirmation, if that makes sense, for the record, I just want to say, I'm pretty sure that every single one of you actually responded to that. And I think that's unprecedented in the history of me doing that with any class. Like, I understand it's just, you might say, well, duh, you were just telling us class is canceled. Like, that's good news. And all we have to do is say yes. Like, what's the big deal? But, the truth is that communication is a big deal. And I think you're the first group that's ever done 100% response on a thing like that. So take that for whatever. And it's not like other groups aren't also excited when class is canceled. It's not that. But somehow every single one of you was able to say yes and say that you got the message, even if you said it a little bit late. So I just want to say I appreciate that. And I am sorry we missed class. Okay, so let's do class. But since it's been so long, I want to flip. I feel like it'd be better for me to flip the order today, because if I'm not careful, I end up talking so much and blah, blah, blah. So you've done like a number of labs now since I've seen you. And I've seen some of you in my office since one of the labs. And of course, I've spoken with Mercedes a lot, but I'd like to hear from you. So I want to go back in the time machine a little bit here. Let's start with, do I want to do this? Well, I was going to say I'd like to hear about lab 3 for the lab 2 weeks ago first, but the truth is, whatever works for you. I know yesterday you had a board meeting, so if that's freshest on your mind and if that will help us get to what we do or do not understand from the material, then that's fine. But basically, I want to turn it to you right now. I'm interested in hearing your description of what's been going on in the lab. I don't mean like whether you like it or not. Exactly. But I mean, like, either tell me what you think the main takeaway is from lab over the last 3 weeks, or the main thing that you're still confused by in lab over the last 3 weeks. So basically, either tell me, I want to hear from one of you, either tell me something that you think I don't need to talk about from the last 3 weeks so you could save us all some heartache. Like, if there's a point that you think has sunk in fairly clearly and you think you're solid on, great. or if you think there's a point that you could tell is supposedly important, but still seems sketchy, I'd love to hear that. Okay, so I'm going to turn it, and then if it turns into a free form discussion, as it sometimes does, that's great too. But let's start with that. Either something that you think is solid and clear from lab, or something that needs clarification from lab. I turn it to you. I'll even put in the chat. In fact, I'm even gonna, well, yeah. Oh, is there someone in the waiting room? Wait a minute. Sorry. I'll repeat my question in the chat in a moment. Okay. Oh, wow. Okay, direct message. Oh, yeah. And by the way, I should have said that. Feel free to use a direct chat if you, I mean, I didn't mean it that, yeah, direct or public is fine. And again, I'm about to read, there's things happening already in the direct chat. Great. I appreciate it. Let me also say to all of you, and maybe we can even do that too. Maybe we'll go in that direction in a second. But if nothing else, just look in your notes and see like what equations did you get from the last 3 weeks and just tell me that. I mean, that would help me. I mean, I know in principle, but I know what's supposed to have happened, but I don't know what landed in your brains. So if nothing else, I'm asking like what equations seem to be of interest these days, and then you could tell me whether they're clear or not. And I think, you know what, honestly, 2 people have already gone the direct chat. So you know what I'm going to say? I would like to hear from everyone. Check this out. You'll check it. I want to hear something from every single one of you in the direct chat, just something. So anything from the last 3 weeks, either an equation that you think you were supposed to have learned. You don't even have to tell me if you think you understand it or not, but tell me something from lab from the last 3 weeks. Every one of you in direct chat. I may or may not respond directly. Okay, but it's just a report. It's not a test. I mean, you're just reporting. I'm not testing you. But since 2 people already went for the direct chat, which I appreciate, let's just do that with everybody. Okay, let me see. Oh. Oh, interesting. Stuff in the chat is already interesting. I'm just thinking about it. Okay. Okay, cool. This is helpful. I'm going to wait till I literally want something from each of you. And I appreciate the nice comments that some people make. You don't have to tell me like whether you are happy about it or not. I mean, like, I'm not asking you to, but just like, just tell me what you think the content was that you did or did not get from it. But no, cool. 3 of you have responded. I totally appreciate it. I'm going to wait till everyone says something just because it's been so long. I kind of I want to know where we all are. Okay. Cool. All right. I'm going to start responding. But I am going to wait till everybody tells me something. It's like that kind of day. Mm. Oh. 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 Okay, this is great what you guys are gonna be. I mean, obviously we'll I mean, I know this is not efficient, but boy, I'm getting a lot on my side. So we'll, as soon as I'm done responding to every single one of you, we'll start again, but wow. Oh, oh, okay. 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 I think, wow, you guys really, all right. And have I, now, technically, I'll say, technically, I feel like there's like one or two people that still haven't said anything in the chat. I'm not trying to shame them or anything. What I've gotten in the chat is it's kind of astounding. Well, it's very, very good, very helpful, like way more than I might have expected or asked for. So I just want to give a minute more to the couple of people that haven't responded yet, but just in case they're thinking or something. But I have heard from a lot of you, so I could probably work with that. I mean, again, just to make sure that we're on the same page, let me say, so, and hopefully I've responded to each one of you. If you put something in and I didn't respond, if you put something in and I didn't respond, please put it in again quickly, or just say like, yo, scroll up, prof, or whatever. But I think I'm now in a dialogue with each one of you, which it's like the one thing we can't do in regular class. It's kind of, this is like the one feature that it still blows my mind, this direct chat thing. Anyway, but the couple of people that haven't said anything in the direct chat yet, could you maybe just put in the direct chat, like, I don't feel like talking right now, or just something to show me that you actually do know what's going on. And if you don't have anything to say, fine, you could just say, I don't have anything to say. But since so many people are involved right now, it would be great if we had if we had unanimity. Okay. No, okay. Okay. So is that just about it? Okay. Okay. But at least, but really, I had a whole, believe me, it may not ever look like it, but I had a whole plan. I always have a whole plan for class, but right. But I'm going to toss some of it aside based on what you all just told me. And that's always better anyway. So I think I've heard from just, all right, I think I've heard from just about every one of you. Okay. Yeah. So, wow. All right. So you've told me some really interesting things here. First of all, some of you in the chat actually, and I'll make this clear, I wasn't asking only for complaints or concerns or compliments. I mean, I was kind of just trying to see like what it is that you know at this point, or feel that you know, or don't know, whatever. And I got that. Like a lot of you actually just in the way, some of you were giving me the exact equations that you feel you're on top of now, and that was really helpful. And then some of you were telling me about issues that have come up. Now, it sounds like there's actually been a lot more success and comfort than there sometimes is. So that's good. I think I want to go in order. Okay. We're going to go sort of in order of what I heard in the chat. A number of you seem to have told me in the chat that in the board meeting yesterday, this is my sense. Now you tell me if I'm wrong. You told me that the board meeting yesterday was maybe a little bit more conversational or more active, that the groups got switched, which is great. The groups got scrambled around. And so it sounds like maybe more people felt comfortable getting involved in the board meeting discussion yesterday than the first time. That's great. It still won't be the last time you'll do that. But it sounds like there was a healthy, or it sounds like there was confusion or discussion and sorting out of particularly of some physics 101 issues, particularly speed versus velocity, which is great. Let me, and first of all, I hope I understand this correctly. I'm saying this slowly because I want to represent you correctly. Let me say that if you're having a board meeting and I'm going to turn it back to you in a minute, but if you're having a board meeting in 102 and a bunch of people are talking, and then what emerges is some kind of disagreement or confusion or lack of resolution over some kind of concept that seems like a 101 concept, then the board meeting is totally succeeding, like honestly. And I'm not just saying that. The goal of a board meeting is to uncover the fundamental conceptions that maybe have gotten cloudy or maybe never got ironed out. It is good board meetings take us backwards. They feel like they're going backwards. In the long run, I don't feel like, I feel like it's totally forward motion to do that, but you're trying in a board meeting to find messes that have not been cleaned up and that are sitting underneath all the other stuff that we're piling on, right? The idea is so the whole thing is like, if we've been piling knowledge on top of misconceptions or confusions, all the knowledge that we're piling on top of it is totally rocky and unstable and may feel more clear than it actually is, and it might be actually deeply inaccurate. So the reason we do board meetings is to dig underneath and see what. So first of all, if you feel like in any way, a bunch of you were unearthing something that you feel like should have been straight in 101, good. That's what you're supposed to do. And don't be disappointed for a minute that it was like a 101 concept. To be really honest, and I want to hear more about it. So I want to straighten it out, whatever it is. I'd like to take a moment, unless it is straightened out. It sounds like there was something about speed and velocity, at least as it gets applied to a wave, that got rocky. Could someone, either in the direct chat or the public chat, can you fill me in a little bit more? Like, unless you feel like now it's all straightened out, is there something that I can help straighten out about speed or velocity as an either in general or as it applies to a wave? All right. Going raise your electronic hand if you agree that, oh, someone's here. Raise your electronic hand if you agree that the issue of speed and velocity came up during your board meeting. Like, is that true? Do I understand that correctly? Raise your hand if, okay. Okay, that's a number of you. All right, thank you. Awesome. Now, okay, now put your hands up. Okay, that's helpful. Thank you. Now, I'm not, again, I hope you understand this one. I'm not testing you. I'm literally just trying to work. So now put your hands down. And my next question, and I hope it's clear too. I always have things I could talk about. I think you realize that. Like, literally, I could happily talk about any of this stuff, right? But what I want to do is talk about what I need to talk about, what you need me to talk about. So, but I don't care what it is, as long as it's helpful. So my next question is, honestly, raise your hand if whatever the speed velocity issue was, raise your hand if you think it's now resolved and it's fine. Like, because if that's the case, that's fine. But raise your hand if you think it's fine now. Oh, okay. Well, that's one per, okay. Okay, fine. I'll take that as a, I mean, all right, okay, put your hands down. Okay, maybe this is now an on-the-spot question. Maybe I'm being obnoxious, but now I'm going to ask just to make sure. Okay, you can put your hands down. Thank you. Raise your hand if you think it's not fine. Raise your hand if the speed velocity issue, whatever it is still unclear in your mind. I knew no one was gonna. All right, of course no one's gonna. All right, I'm gonna take you at your word. I mean, we all know. Oh wait, oh you are. I'm sorry, Jake. You're raising your hand, or that's.
Yeah, I have a question. So I think that I don't know if there were other teams, but I know that my group was one of the ones that used velocity mistakenly, and it was pointed out that it should have been in speed. For acceleration, is that a term that can be used as both like for vectors and as like a scalar measurement, or is that only used as a vector?
Oh, okay. Great question, and thank you. And also, other direct chat. I saw the other person in the direct chat. I hear you. I see you. Okay, and no apologies necessary. Okay, that's a great question. So the answer is right. There are not two different words for acceleration. For acceleration, right? That's an English weirdness. With speed and velocity, we have two different words. Speed is the magnitude of the velocity vector, or speed is defined to be the magnitude of the velocity vector. Acceleration, there just simply are not two words in English. When we're trying to do physics, but we're speaking in English, what we'll sometimes say is the magnitude of acceleration, or we'll say the acceleration vector or something like that. But that's totally true. That's an unfortunate ambiguity in English, that there, yes, the word acceleration in and of itself could imply either of those two things, vector or scalar. That's right. And I will say that sorry, hopefully that answers it. Now, I it's interesting, dude, just from the way that Jake just said that, like, so my sense, and if it's resolved, I'll move on. I don't want to waste anybody's time on something that is resolved. My sense is it sounds like in the board meeting, let me just ask this directly. We're talking about the velocity or the speed of a wave in the board meeting. That's what you all are talking about, right? Like, it's coming up in the context of a wave moving. Am I right about that? Or is that not what we're talking about?
No, that's correct.
That's correct. Okay. So I will say I'm a little bit intrigued. It sounds like some groups were only using the word speed, and then the other groups somehow corrected them or said, no, you got to say velocity. I'm not 100% sure. I mean, unless you guys tell me. Yes, velocity is a richer, more precise term. Yes, the term velocity includes more than speed. It includes direction. When I'm thinking of a wave and the stuff that I'm planning on saying today to all of you, or the stuff that we need to learn, it's not 100% clear to me that distinction matters so much. It is a distinction, but I guess to be really blunt, like, we really care about that distinction when things change their direction. Like in Physics 101, when you throw something up and it comes back down, it's really kind of important to recognize that it's, say you call up positive. It's very important to realize that when something goes up and then it comes back down, its speeds are going down, then its speeds are going up, whereas its velocities are always going down. let me just say that again for everybody. I know this is 101 now, but just to be clear, like if velocity includes direction, and if we call the upward direction positive, let's say, right? When you throw something up and it comes back down, and I want anybody to stop me if they don't buy this once I've said it. I don't care that it's 101. And I don't care. I mean, whatever, I don't care. If I throw something up, say at 50 miles an hour in the up direction, then its speeds are going 50, 40, 30, 20, 10, 0, or like whatever, right? 50 meters per second, let's say. So the speeds are going 50, 40, 30, 20, 10, 0. And then the speeds are going 10, 20, 30, 40, 50. So speeds are going down and then speeds are going up. But velocities are going like positive 50, positive 40, positive 30, positive 20, positive 10, 0, then negative 10, negative 20, negative 30, negative 40, negative 50. So the velocity numbers are always going down, right? They're always going down by 10. They're going from the positives lower and lower into 0, and then increasingly negative numbers, right? And it's for that reason we can say, and we must say, that the acceleration is a constant. The acceleration is always pulling the velocity numbers down, whether the thing is moving up or moving down, right? That distinction, right? Whereas the speeds are going down and they're going up, but the velocities are always going down. Therefore, they're always changing by the same amount, always by a negative. Therefore, the acceleration is always negative 10 or negative 9.8, whatever, meters per second squared. That's a very important distinction between, that's where the distinction plays out between speed and velocity, and our recognition that velocity really does care about direction, and therefore we could make certain conclusions about acceleration and force and all that. However, I'm saying all that, well, first of all, wait a minute, let me pause right there. Well, no, I won't. I'm saying all that to say, now, it's not totally clear to me that in the waves that we're talking about here, unless you guys were talking about waves that went there and then went back, which waves can do, but I'm not, if you're analyzing a wave that was making a round trip or turning around or somehow in an important way going in more than one direction, then then it's like really important to keep track the distinction between speed and velocity. But if you weren't, I'm not saying anybody was wrong. Like I wasn't there. And if you're straight, you're straight. But I will say that if anybody's criticizing themselves or thinking like, oh God, I can't believe even here I am in physics 102 and I like didn't even get it straight. Like it's not 100% clear to me that a physicist would have made a big deal of that distinction in the context that you were in. If I understand the context right. Oh, okay. Okay. No, that's very honest. I'm seeing things in the chat that are very honest. Okay. And I do. Wait, okay. Oh, now I feel bad. Oh my God. I need therapy. I shouldn't make jokes about that, but clearly I do. Wait, because I'm seeing things in the chat that are now making me feel like no. Like someone is saying that they question those terms because we wanted to really get deep. But and I do absolutely. And look, again, even if the whole discussion you had forced all of you to really get straight speed and velocity, the Quark plus America, definitely, like that is the point. You do want to go wherever you go in those board meetings. Just like right now, I'm going with whatever I'm seeing in the chat. I'm not saying it was a stupid discussion at all. Clearly not. And like about 3 people in the chat reported a similar thing from the discussion. So obviously it landed with you people. I'm not saying that was a waste of time at all. I am saying that if anybody was beating themselves up in either direction, don't beat yourself up for having brought it up. It sounds like a great thing to have brought up. But also, if you were one of the people that originally was saying speed instead of velocity, also that probably doesn't mean that you don't understand waves or something. But okay, no, this is great. Okay, but wait. Hold on, I'm going to just respond quickly to, I just want to make sure everybody's cool, and then I will go. But this is definitely telling me where I should go in a moment with, okay. All right. Okay, but this is good. I think I know where I want to go with this now. Again, I'm going to try, I'm just trying to balance here. I want to give you content. I want to give, advance the curriculum with you. But I don't want to just talk at you for 2.5 hours. So again, I'm going to start talking a little bit now, but stop me whenever. Well, yeah, okay. Okay. First of all, do we recognize this? Is this equation fair for me to write? Like, does this look like something we've been dealing with in lab? Like, you recognize all the terms in this equation? Yes, thank you, Eugene. Okay. Yes, thank you, Sulady. Okay. This thing here. Okay, cool. Oh, thank you, Nicole. Awesome. Thank you. Oh, and thank you, Ariana. I didn't see that. By the way, I love Ariana's avatar. I love all the avatars. I hope it's still clear to all of you. Like, I'm not, Ariana, you can submit for points for that avatar. Like, there's a portal. Okay, awesome. Okay, excellent. And you can get points for that. Like, there's a portal for submitting that. Okay, cool. Okay, awesome. Okay. Can anybody, that last term, first of all, okay, here's a dicey question. You can put an answer in the direct chat, but it's a concrete question. This is like a right or wrong answer kind of thing. Okay, but remember, you can get points even if you can get points, especially if your answer is wrong. I want to know that phi, that symbol is called phi right there. What units must that phi thing be measured in? Like, that phi thing is just any number. It's a numerical constant. It could be any number that doesn't change, right? That's what it stands for, some kind of number, but a number measured in what units? I'm going to wait till I get at least 2 answers in the direct chat. I don't care if they're right or wrong, but that was fast. Oh my God, that was so fast. I love this class. I did not see. Oh, that was one thing in the chat. Okay, that's one person. That's one person in the chat. Sorry, I was behind in the chat. I'm going to wait till I get at least one more person in the chat. I am going to say to the one person who's in the chat right now that he or she is correct, which is awesome. But I don't care whether it's correct or not. I do, but I want one more person to try to answer in the direct. Okay, that's fair enough. Someone's saying they don't remember. Fine, you don't remember. I will give you a hint, though. I think it's a matter. Generally, I do physics because I can't remember anything. The thing about physics is it's really not about memory. If you notice, it's like if you stand back and look at the actual amount of material that you've learned in the conventional sense, it's like very little that we're asking you to know. But what we're trying to do is set up things so that we can figure out a bunch of stuff about the universe. So I think this is figure outable. I'm saying this to everybody. Like I'll give you a hint. The units of it have to be the same as whatever the units of omega times t are, right? Because you can only add feet to other feet, or inches to other inches, or pounds to other pounds. So whatever omega t is what phi would have to be. And I might go further to say that whatever that is it has to be the kind of units that you can take the cosine of. There's only one, if that helps, but okay. Oh, that's okay. Now there's 3 people in the chat, and one person's being totally honest and totally clear, and I appreciate it. And 2 people are being also totally correct. So yes, I'm going to say this. That's great. That's great. The units of that. And there's more. Yes. Well, and someone just saved me a lot of time in the chat too. Someone just explained in the chat. That's awesome. Yes, way to go. God, I wish this were like a podcast or so. That would make no sense. But I guess I'm just saying I wish I got to listen to this rather than. All right, anyway, yes, some people in the chat are psyched, and people in the chat just explained in more concisely what it is that I now wanted to explain. And they're totally correct. Like, yes, this thing must be measured in radians, because omega t is measured in radians, because omega is radians per second and t is seconds. So the seconds cancel. So omega t is in radians, and omega was designed that way. It's there so that what we have in the parentheses are radians. You can only take the cosine of something measured in radians. But remember, what a radian is a portion of a cycle. So what was one person in the chat or two people in the chat are saying here is, right, what phi stands for, so I'm agreeing with people are, this is my words for what people are saying in the chat. Phi is, we call it the phase constant or the phase shift. It's a head start or a delay with regard to cycle. Like so I'm going to show you an example. It's how far into the cycle an oscillator started. Now, what does that mean? I mean, if it's a cycle, like, what does that mean? What we're really asking, what we're really talking about is at what moment we started our stopwatch. Where in the cycle was the oscillator when we started paying attention and timing? That's what we're really talking about with phi. So I want to give you one quick, you'll see why I'm reviewing or explaining this, but it does sound like there's already some good understanding of it. Oh, I'm looking in the chat. Wait. Oh, you guys really do get this, or at least one person. No, you really. Wow, I'm looking in the direct chat. There's okay. I'm gonna try to do this a little bit faster because it does seem, I'm impressed, guy. Like, it does seem like you know what I'm talking about, and this is not a joke material. I will I'm going to make sure everybody that we're all on the same page together, but I'm seeing from at least some people in the direct chat that I'm not out of nowhere with this. So I'll try to speed this up a little bit. But look, for everybody, just to be clear. Oh, wait, and I see I'm using a slightly different word from what you're, hold on, video for questions, right? Right, it started. Oh, yeah. Okay. So, but yes, in the labs, yes, you guys are, and it's different people in the chat too. You totally just, thank you. I was gonna, all right. Yeah. Yes. Hold on. Sorry. Oh my God. This is not, when I started being a teacher, I did not think teaching was going to look this way, but maybe I didn't watch the Jetsons enough. Hold on. All right, so you guys are saving me time, and keep this coming. If it helps speed me up, that's great. Like what? So here's what I'm getting from the chat. Okay, first of all, yeah, fee stands for whether some kind of head start or delay. In the labs, you may very well, and in life, in a lot of like internet sites and textbooks, you could think of fee as like a starting position. You totally can. It's like where in the cycle you start, right? But that means where in the cycle you start when where in the cycle you start, like where in the cycle you are when t equals 0. So just another way you could look at it, if that makes sense to you, that's great. And it does make sense to me. But from an experimental point of view, or from a like actually visualizing this point of view, I mean, the one thing I just want to make clear is like these are cycles, they're going back and forth forever and stuff. So it's sometimes for some of us, it's hard to visualize. What do you mean by where the thing started? Like, isn't it just going on and on forever? And in a way, the part that we can control is where it, you could say it as where it was when we started the experiment, or we could say when we decided to start the experiment, where it was. It's the same thing. But what I'm trying to say is if phi is 0, what that means is that when we started our stopwatch, the object was at the beginning of a cycle, meaning the positive amplitude position. Like if you go all the way back to homework 1, where we had a mass that's on a spring and it began, like we held it at rest at position 15 centimeters from equilibrium, right? And then we let it go and it went back and forth and back and forth. So we started our stopwatch when the thing was as far as possible from equilibrium. And then it started doing cycles from there, right? That's like our standard conventional way to begin a cycle is at the amplitude position, at the maximum displacement. So yes, when phi equals 0, what that means by definition, when phi equals 0, that means at t equals 0, x equals amplitude. And one person in the chat was telling me some English about like how you understand this, and a different person in the chat totally just nailed the math. Thank you. Right. So that's an example of having no phase constant. Now, there's a reason I'm doing this. It's not just to review, like I want to build something from this, just to do however, if theta, for example, equals pi over 2, okay, pi over 2 radians, right? Then let's look at what that would mean. Then y, sorry, we're doing y or x, we're doing y, okay. Then y equal, whoa. Hello, what just happened? Whoa, sorry, that's bad. 1 second. Okay. Right, if you have a phase constant or a phase shift of pi over 2 radians, right? Well, or I'll just do it. Then the math would be y equals a cosine, like then at t equals 0, we again have omega times 0, but plus this pi over 2, right? So we have y equals a cosine of 0 plus pi over 2. So now let me ask you, maybe in the direct chat or whatever, what is the Now, this is where you want to picture the unit circle, or picture that long lecture that we had like 4 weeks ago where I bored everybody to tears about the unit circle and all that stuff. But like, remember, yes, yes. So what she or he in the chat is saying is, and I'm totally impressed, and and you guys are, by doing this in the chat, even if you still think I'm going too slow, I'm actually going faster than I otherwise would. Like, it is helping. The more you chat with me, the more we get on exactly the pace that you need me to be on. Like, okay, but oh, good. Me too. No, me too. Totally. I'm very happy. And again, for those of you who think you totally get this, I am ultimately, this is part of a point I want to make. I'm not just reviewing this as an exercise. So what this means is, right? So pi over 2 means a quarter cycle, right? Because there's 2 pi radians in a cycle. So there's 1 pi radian in a half cycle. So there's 1/2 of pi radians in a quarter cycle. So it totally makes sense. So if someone says they have a phase shift or a phase constant of pi over 2 radians, what they're saying is that the stopwatch started when they were already a quarter of the way through the cycle. They weren't all the way at the other side, but they were at the middle, at equilibrium. That's a quarter of the cycle. If going all the way to the other side is half a cycle and coming all the way back is a full cycle, right? So it makes sense. So just to be clear, and it sounds like it is clear to at least some of us, what phi is all about is, yes, where you're starting in the cycle, or when I started my stopwatch for you in the cycle. Okay, now, okay, that's review, I guess, technically fine. But good. But again, just so you know, like, that concept is not always that quickly clear to people in other classes that require calculus and stuff like that. So I'm glad you get it. And if you don't get it, you could still in the chat tell me you don't get it. Oh, wait, what are they? Oh, what are they? Okay. Oh, okay, wait. Oh, okay, wait. No, I just got in the chat what I needed to get. Okay, so wait, maybe I'm okay. Wait, okay. So not everybody's on the same. Fair enough. I appreciate. Okay, hold on one second. Wait, hold on one second. Where? Okay, this is what I'm saying. What I'm saying, forget about anybody in the chat. What I'm saying here on this board, what I'm trying to say, and I do want to ask in a minute, new people tell me whether it makes sense or not. I'm saying that symbol phi, this symbol right here, according to the 2 different examples I'm saying phi represents what kind of head start or delay an oscillator has in terms of the cycle. It represents where in the cycle the oscillator was when the experiment began. So if phi is, so it tells what phi is about is where is the oscillator at t equals 0. Phi tells us where the oscillator is at 0, at t equals 0. Specifically, what I'm saying is, if phi is 0, then that means when the experiment started, the oscillator was all the way as far as possible from equilibrium. Like in homework 1, like the mass, like when the experiment started, when t was equal to 0, the mass was 15 centimeters from equilibrium. It was as far as it was ever going to get from equilibrium. So then the experiment started and it went all the way to equilibrium, and then all the way to 15 centimeters on the other side. And then it came all the way back, and it kept doing that forever. So in homework 1, we started the experiment at the edge, so to speak, of the cycle. And when you start at the edge of the cycle, we call that no phase shift, that's no head start, no delay, phi equals 0. But if phi so that's the phi equals 0 case. But if phi, for example, equals pi over 2 radians, like phi is always measured in radians, but you got to remember that a radian is a portion of a cycle. So if phi is equal to pi over 2 radians, what that means is that the object was already a quarter cycle into its journey when the experiment started. It means we started our stopwatch and the object wasn't at its edge. It was already in the middle of this back and forth journey. And when I say the middle, I mean like y equals 0. I mean the equilibrium position. What I mean is a cycle starts over here, starts at amplitude, it goes all the way to amplitude on the other side, and then comes all the way back. That's one full cycle. Therefore, a half a cycle would be going all the way over there. That would be, so if something were all the way over there already, when we start our stopwatch, we would call that a phase shift of pi radians. But if something is, because a pi radians is a half of a cycle, all the way there, but not yet coming back is a half cycle. There and back is a full cycle. There and back is 2 pi radians. So if something has a phase constant of pi over 2 radians, that literally means a quarter of a cycle. Like 2 pi radians is a full cycle. Pi radians is a half cycle. Pi over 2 radians is a quarter cycle. It means when we started our stopwatch, the thing wasn't here. It was right here already in the middle. So that number, whatever the number of phi is a measurement of where in the cycle you are when the stopwatch starts. And we're measuring cycles with radians. 2 pi radians is a full cycle. Pi radians is a half a cycle. Pi over 2 radians is a quarter cycle, et cetera, et cetera. Does that, I'm going to pause for a second. The person, oh, okay, great, thank you. Okay, cool. Okay, I really appreciate you. I'm getting on. This is great. I mean, cool. Okay, good. Okay, no, I know. And for the record, no, and I, okay. So now why am I saying all this? Here, so that's what phi means, right? But okay. Oh, okay, cool. I'm seeing the chat. Okay, sometimes there's no such thing as overthinking in this class. You're totally cool. It's all good. It's all good. So but you can, if you feel like you're getting what I'm saying, you guys can tell me if I'm going too slow, or too fast, which both, honestly, I've just gotten both of those kinds of feedback in the last 15 minutes, and I really appreciate both. I mean, I think it's really helpful. So where I'm going with this is the whole idea of a phase constant in and of itself. It's like a stupid idea if you only have one. It's not stupid, but it's not a necessary idea if you only have one oscillator. Because if you have one oscillator, you start the clock wherever you want, or you start the oscillator wherever you want, whatever's most convenient, and you call that 0 and you go from there. Like, there's no actual reason to care about this or to get bogged down in these details if you only have one oscillator. Where this comes into play, where this becomes necessary and meaningful, is if you have more than one oscillator and they are not starting in the same place. So you might still say wherever one of them started is 0, but if the other didn't start in the same place in its cycle, then you can't call them both 0. So you have to track where they are in their cycles with this term. Okay, so this is all about multiple oscillators. And what it sounds like you really did pick up from from last week's like Make a Wave lab. What I think you picked up, but I want to just put in my terms now is so we're going to consider those are supposed to be springs. I don't know why they're becoming like smoke detectors, but okay. Now, what I'm drawing here, it is true on the one hand that at least one person in the chat said something in English to the effect of what I'm drawing here. So that's good. So on the one hand, I have some reason to believe that some people have some familiarity with what I'm about to say. Some. On the other hand, I'm not sure that that means it's 100% clear to everybody. Also, I want to take this into a slightly different direction now. So hopefully everybody can get something out of this. Yeah, hopefully what I'm saying is now let's imagine. So wherever you are with this, whether you feel like you know what I'm about to say or whether you don't, like just look at it with fresh eyes if you can. I'm saying, let's imagine that we have a bunch of identical oscillators set up to oscillate, along a vertical axis, for example. And I say they're identical, meaning like they have all the same M, they have all the same K, which therefore means, now from earlier weeks, if they all have the same parameters, the same material properties, constant material properties, if they all have the same parameters, then they're all going to oscillate at the same angular frequency, right? And let's also assume that each one of them will oscillate with the same amplitude, call it A naught, that's just a way of saying, assume that A is a constant. So all of these oscillators are designed to be identical. they're all going to oscillate at the same rate and throughout the same span on vertical axes. And then we spread them all out uniformly along an x-axis, like literally uniformly, like equidistantly. So like the first oscillator is at the edge of the meter stick at what we might call x equals 0, right? And then the next oscillator is at 1 centimeter from the first one. And then the next, so it's at x equals 1, like 1 centimeter. And then the next one is at x equals 2, like 2 centimeters, et cetera, okay? So everything about these oscillators is identical, except we start them all at a different phase, at a different place in their cycle, right? Kind of like the idea that we were just talking about a minute ago. In fact, for the purpose of this example for right now, let's even assume that we stagger them in phase by a constant amount. Well, I definitely want to assume that we stagger them in phase by a constant amount. I'll be more specific about that. Let's assume, for the sake of this example, that they are staggered in phase by a constant amount of pi over 2 radians per meter. Now, what that would mean, like, so for this example, where can I write this? Yeah. Let's assume that for every meter you walk over to the right, you add another pi over 2 radians to the phase constant, right? So in other words, let's assume that the first one, the 0th oscillator, we'll assume has a phase constant of 0. So the minute we start our stopwatch, it's at like the amplitude position. It's at the highest possible position that it's ever going to be, right? Then, and it starts oscillating at omega. Then the next one, let's assume at that first moment at t equals 0, when the 0th one was at the amplitude position, let's assume that the first one is not at the amplitude position, but it's at the equilibrium position. It's like pi over 2 advanced in phase. So the next one is pi over 2 in phase compared to the 0th one. Now I'm going to go one step further just to make sure this is absolutely clear. Then I want to turn this into equations, which you sort of have seen, sort of have not. Assume the second one now is another pi over 2, like staggered in phase. So the next one is, it's not at the top amplitude, it's not at the equilibrium, it's at the bottom amplitude, right? So it's one more pi out of 2, it's one more pi over 2 phase compared to its immediate neighbor, but that means that it's 2 pi over 2 radians away from the original 0th oscillator, right? In what I'm saying, and I'm going to stop you in a second to make sure. What I'm saying is each one of these oscillators, if they're all staggered by pi over 2 radians per each meter, then we can write down for each of these oscillators You're with me so far, right? I could write a separate equation for each one of these oscillators, and each one of these equations would appropriately describe each oscillator. Each oscillator literally has the same equation, except for its phase constant. And its phase constant is just a multiple of, in this case, pi over 2, right? Is everybody still with me? So, like, okay, cool, awesome. Thank you, direct check. Oh, that's 2 people, awesome. 3 people, awesome. Oh, or that means you do understand that's required. Okay, great. Okay, so I'm gonna go. Um, Wait, I'm just looking at the chat. What's happening in the chat? Okay, cool, cool. Okay, so what I'm going to do now, if this is true, that each one of these oscillators can be expressed by an individual equation that differs only by the amount of phi, then we could collect, in this case, where the phi is increasing by pi over 2, we could collect this whole thing into one equation, right? We can capture. Right with me so far? I'm saying in this example, we could capture that whole equation. I mean, we could capture all of those equations into one and just say y equals a cosine omega t plus pi over 2x, meaning like, because if you look back at all the individual equations, if you want to know, well, hold on a second. Right? Like, just to be clear, my hair is getting, just to be clear, we could write this equation. We're not done. We're almost done with what I'm trying to do right now. But I'm saying if we, for this situation where we were increasing the phase in steps of pi over 2 radians, we could capture this whole collection with this one equation. And what would this one equation do? It would say, for as long as you plug in a t and an x, we can spit out a y. We can tell you how high a mass is as long as you tell us what time you're looking and you tell us which mass you're looking at, like how far over on the line you're looking. But like so you pick a time, t, you plug it in. And then what we're saying is, okay, we've got an oscillator here. You tell us the time, we'll tell you the height. But to know what phase of the oscillation we're in, you got to tell us which oscillator you're talking about. If you're talking about oscillator number 1, then we know it's got a phase constant of 1 times pi over 2. It started in the middle. If you picked a phase constant of 2, if you picked the second mass, the mass at 2 centimeters, we know that thing started with a phase constant of 2 times pi over 2. It started with a phase constant of pi. It already started halfway into its cycle. So we plug that in, right? Like this would be one equation that would predict vertical position as an output as long as you input time and horizontal position, right? And it's just basically saying, okay, the phase constant of any given place you look is a multiple of pi over 2, right? Right? So the only thing I have to adjust now is I have to say, okay, if that's clear so far, I have to say, oh, sorry. Everything I just said is correct. It's all correct, but it's all based on this example where you keep stepping by pi over 2 radians per meter, right? Like the first thing was at amplitude, the next thing was at equilibrium, the next thing was at negative amplitude. It's nice and clean and vivid and easy to picture because I happen to pick the number pi over 2 radians, like from our earlier example. Pi over 2 radians is a quarter cycle. It's kind of easy to picture things in quarters. I mean, comparatively easy to picture things in quarter cycles. What I want to say now is we can make this whole setup, and it doesn't have to be specific to pi over 2 radians per meter. It could be any number of radians per meter. Let's call
Professor, I can't read that.
oh, sorry. Oh, yeah. Wait, okay. Yes. Good point. Okay. Wait. Thank you. Okay. Thank you. I appreciate it. Or maybe you can't read this either. Okay. What I'm trying to, and thank you for the handwriting thing. Hopefully this, so what this says, I mean, just to read it, it says, let bracket K equal bracket radians per meter. What I'm saying right there is, let's introduce a new constant called K. Now, let me pause right there. We already have a K in this class, the K from Hooke's law from spring stiffness. That's called K. Unfortunately, this thing is also called K. That's just the way it is. They're both called K. It's two completely different Ks. So I try to distinguish them by putting serifs on this one. You might say, why don't you make it lowercase Yaverbaum? And you can, except that we have another K coming later in the class that I generally make lowercase. I don't know what to tell you. There's a lot of Ks in the world. So yes, so this one I make cap. I mean, maybe I don't. Mercedes might do it differently, and it's like you could do whatever you want. I do it capital, but with serifs because our other K was also capital, but I didn't put serifs. Well, however you want to do it, but this is K, okay? And this K stands for any number of radians per meter. It stands for, it's like whatever you understood a minute ago, hopefully about. Oh, okay, cool. Okay. Whatever you were understanding a minute ago about pi over 2 radians, I'm saying that didn't have to be pi over 2. That was just like the clearest example I can imagine. But if you just imagine this idea that we're putting a bunch of oscillators next to each other, and they're uniformly distributed along, say, an x-axis, right? But each one of them is free to oscillate along, say, a y-axis, right? So you spread out all these oscillators. They're all equidistant. They're all like next to each other. They're all made of the same material. So they're all going to oscillate in the same way, like at the same rate and with the same amplitude, let's say, right? But the one thing you do is you set them up so that they're all out of phase with each other, but they're all out of phase in a pattern. Like they're all out of phase in the simplest possible way you can imagine. And I want to emphasize that. But in fact, well, I'll emphasize that again in a minute. But so they're all like, in other words, no, I'm going to emphasize it right now. Let me back up for a second. What I'm really trying to say here, is this is, in a way, the simplest possible meaningful way you could arrange a collection of identical oscillators. What I mean by What I mean by that is, just imagine, like, whether you know things from lab or not, like, just go blank slate in your mind for a second. Just imagine that I want to talk about a bunch of oscillators now. I want to study a bunch of oscillators. Like, I'm sick of one oscillator. I think I know everything there is to know about an oscillator. Now I want to see if I can somehow, in any way, take advantage of putting a bunch of oscillators together, okay? So I take a whole bunch of oscillators that are identical, and I put them and I arrange them all in a line on the lab table. And now I want to set them in motion, oscillation, in the simplest possible yet meaningful way I can. So what I mean by that is, if I did it literally the simplest possible way, I could set all of these oscillators in motion from exactly the same place at exactly the same time. And I could have them all go like this. Right? That would be literally the simplest thing I could imagine doing with a whole bunch of oscillators. I could have them go up, down, up, down. Now I could do that, but that's not worth studying. It's not really worth thinking about or even doing, because if I did that with a whole bunch of oscillators, in every way, shape, and form, that would just be equivalent to having one enormous oscillator just go. I might as well just have one really wide spring going up and down, right? And there's nothing wrong with that. But then why did I buy 400 oscillators? Why did I buy 400 springs, right? So we're going to go one step level more complicated. We're going to say, let's arrange all these oscillators, but let's get them all started at different places. Like when this one's here, have this one be there. And when that one's there, have this one be there. But, so, right? So I'm making it one step more complicated than what mathematicians would call the trivial solution. Like, this is so simple that it's stupid. It like literally doesn't take advantage of the ingredients of my setup. But I go one step more complicated and have them all go in different phases. So now something maybe interesting will happen. At least now I'm taking advantage of the fact that I have all these oscillators, but I'm going to do that in the simplest way you can imagine. Like before you look at all the math or get intimidated by the math or whatever, if you just picture in your mind the simplest way that all these oscillators could be out of phase with each other, the simplest way would be is if they're each out of phase by the same amount, right? Like, in other words, I'm asking, whatever you think you're picturing right now, I think it's right. I'm not saying anything more complicated than just, well, this one's here, this one's there. And while this one's there, this one's there. And while this one's there, this one's there. And eventually, of course, it would cycle around again because, you know, if each one is separated by, say, a quarter cycle, then by the time you get to the fourth one, you've done a full cycle. So you're going to be back to where you started. So I'm saying, imagine that situation, but imagine now that there's no rule that says it has to be a quarter cycle between each two. It could be a third of a cycle or a sixth of a cycle or whatever that is, whatever that number of cycle portions that per each meter that you look across the arrangement, we're going to call K. K is the number of radians per meter. Again, remember, radian just means portion of a cycle. So K stands for by every time you walk to the next meter or the next centimeter or whatever, every time you walk to the next oscillator, how much are you advancing in the cycle? Whatever that amount is, we're calling K. K is the step of phase staggering, right? And it's measured in radians per meter because of what I just said, that it's like for every meter that you look to the right in this arrangement, how many more radians advanced are you in the cycle? So if you did that, right, the entire collection would be captured in this one equation. The entire collection of oscillators would be captured in this one equation, which is a function of two variables, right? It's a function of two independent variables. Now you have two inputs, two independent variables. You have two independent variables, both driving one dependent variable. The dependent variable is height, vertical position. The independent variables are time and horizontal position, right? That's what this equation is. And there's like a parallel thing going on, like omega is radians per second, K is radians per meter, right? And this would be an equation to capture this collection of identical oscillators staggered in phase by a constant amount, right? That's this equation. But now, if you stand back and watch the action, and you know the answer to this, and someone's here, sorry. So this equation captures a collection of phase staggered oscillators, right? Okay. But I guess I have one of two. If you stand back and look at this whole phenomenon now, what do you see? Like, what do you see? If you stand back and watch this collection of oscillators staggered in phase by a constant amount, like each oscillator is traveling vertically, but do you see anything travel horizontally? Or what's a word for this whole phenomenon? Or let me put it a slightly different way. And I don't know if this came up in lab or not, the thing I'm about to ask, but what's the omega is called angular frequency, right? Omega is angular frequency, cycles per time. What do you know from lab? And you may or may not, what is the word for K? What's it called? And I mean, I'll give you a hint. I mean, what K is cycles per space. But do you know what K is called? Or I'll put it another way. Oh, okay. That may be. All right. So at least one person saying in the chat that it was not brought up in lab. That may well be. That's fine. Okay, I'll tell you. But you know this though, right? You know that omega is the number of cycles that occur per unit time, right? Do you know what K is the number of cycles per unit space? What is the length of space between? So if omega is how many cycles occur per unit time, put another way, omega is for any one of these oscillators that you look at, it's how many round trips it makes per every second. That's what omega is, right? How many round trips it makes every second. That's what omega is. K is how many round trips, how many oh, did I just lose my, yeah, okay. Oh, the board just disappeared. Hang on a second, sorry. Yeah, so omega would be how frequently any one of these goes back up and down. How long you have to wait in time before a mass returns to its original position. Like that's what omega is dealing with. But K is dealing with how far you have to walk before you get to the next mass. How far you have to walk from one mass to the, how far you have to walk from a particular mass until you get to a mass that's in the same position, right? Omega is cycles per time. K is cycles per space. What does this whole thing look like if you stand back and look at it and watch this and watch this one go up and down while this one's going up and down, while this one's going up and down, while this one's going up and down, but they're all going out of phase? What do you see anything go from left to right if you watch this? What have I just created in the spirit of your lab 4 or whatever lab it was last week? What have I just created with all this? What is, yes, thank you. Yes. The thing that I want to make absolutely clear is this thing is a wave, right? And that's a very big deal. And it's a very big deal. And even some of you may knew that I was saying that, and you might have thought I was asking for something harder. Some of you don't know what I'm talking. It's worth me saying 100,000 times to all of you, and it's worth thinking about 100,000 times that when we put a bunch of oscillators together in a very particular way, if we arrange a bunch of time oscillations into a space oscillation, what we get is this new and immaterial and bizarre thing called a wave. We didn't have it before. I mean, you've seen waves now in labs for 2 labs, but we've never mentioned waves yet in lecture. Everything we've been doing in lecture and everything that you were doing in lab until 2 weeks ago was oscillation. I'm saying if you put together a bunch of oscillations in a very specific way, what you get is a wave, and a wave is a very specific, very, very miraculous thing. Let me be clear, or let me try to be clear. But what I'm saying, the answer I'm looking for here is this is a wave. I'll be more detailed about what I mean by that in a second, but this is a wave. And a wave is an unthingy thing. okay, the real point of all this is, and I'm going to write this all down in a second. I'm going to back up in a second, and I'm going to leap forward in a second. But each one of these oscillators that we've been studying for like a month and a half now, till I mean, many of us are, I'm sure, bored to tears. We've been doing all this math and all this detailed analysis of an item called an individual oscillator. An oscillator is a thingy thing. It is a particle. It is a discrete, material, distinguishable, countable, tangible, identifiable, separatable, massive object of the material world. If you put a bunch of these oscillators together in a very specific way, or if nature puts together a bunch of these oscillators in a very specific, highly elaborate, highly mathematically intricate way, all of a sudden what we get is something called a wave, and a wave is not a thingy thing. A wave is not a particle. It's not distinguishable. It's not material. It's not countable. I will tell you what I mean by all that in a minute, but I really want to pause and yell and make a big point of this right now, because what you did 3 weeks ago in lab is you transitioned, with whether you knew it or not, you transitioned from oscillations to waves. And then indeed in the lab like a week ago, you in fact made waves from oscillations. So at some level, I know you know all this. At some level, I understand that you understand that you've already been down this road in lab in a way. But I'm here to tell you, like, by the way, I heard from at least 4 of you that you had a fun time, or that lab went okay when you made waves from oscillations. And it sounds like you understand the equations and stuff, and I'm here to do them in a slightly different way and all that. But I'm also here to say, I'm glad you did that, and I'm glad it didn't confuse you, and I'm glad it seemed solid. But now let's pause and recognize that what you are doing when you make a wave out of oscillations, you are literally creating something immaterial from a bunch of material ingredients. That is weird. That is a big kind of central point of this course is the physics of immaterial, non-tangible, non-massive, non-particular, non-countable entities. And that's what this is. So forgive me if but that cannot be emphasized enough. Let me tell you what I mean. First of all, let me just fill in some gaps right here. First of all, the word that I was looking for that you may not have heard in lab, that's fine. But if omega is called angular frequency, and it's measured radians per second, in other words, cycles per time, K is known as this particular K is known as angular wave number. Because once K comes into the picture, we have a wave. Before there's K, we have oscillation, but we don't have a wave. And even with phi, we don't have a wave. We have oscillation. Once K is involved, we have a wave. In fact, one thing I think you do know, because I think some of you put it in the chat, in the same way that omega is 2 pi over T, where sorry, let me put this. Wait. Hang on. Wait, let me get there's cool things happening in the chat. Give me 1 second, I'll go to the chat. Let me just well, actually, okay. Well, yeah, no, let me finish this and then I'll go to the chat. Omega is 2 pi over T, where T is period measured in seconds. Period means the amount of time of one cycle. Well, what K is 2 pi over lambda. Lambda, where lambda is the length for one cycle. Well, where lambda is called wavelength. for one cycle, and it's measured in meters. Okay. So omega is to time as K is to space. Omega is to period of time as K is to lambda wavelength of space. Period. Okay, I'm going to pause, but we're talking about, I'm saying that, and I'm going to look in the chat, I'm going to answer the chat, but this equation here, once we throw the KX term in, we now have a wave. Please note, I'm going to say a bunch about this. Some of it will be old to you and some of it will be new, even to all of you. Some of it will be new. What I'm trying to scream right now is this equation. I'm saying nature, we just pulled a trick on ourselves. I will go to the chat, and when I'm psyched, there's things in the chat. I'm just trying to say that I'm not trying to trick you, but I am trying to be dramatic. I'm trying to say that that equation on the bottom of the page is a function of two variables. It is our first equation in this class, really in your career in science and math, honestly. It's our first equation where there's two inputs and one output, right? And even 2 pages ago, where we had y equals a cosine omega t plus phi, that wasn't two inputs, right? Phi was a constant. What I've now said is if phi, if that constant amount actually itself is a function of x, if so, now we have like a function inside a function. If now how high a thing is not just dependent on when you're looking, but it's also dependent on where you're looking. And if those two factors are independent of each other, so they're both literally independent variables, they're both inputs that drive an output, but also they're independent of each other. They just independently drive that output, right? That once we throw this KX business in there, once we say that oscillation is occurring in time and in space, that cosines are occurring in time and in space at the same time, then we now have a wave, right? And I still haven't even really said really what a wave is, but I'm saying that equation was built as a description of a collection of oscillators, but I'm saying a collection of thingy things. But if we collect them and arrange them in exactly the right way, then they give rise to an immaterial thing called a wave. I'm literally saying, and I'll shut up and go to the chat, that equation on the one end is the equation for a collection of particular oscillators, but it's also the wave equation. It's the equation for the motion, the propagation of a wave pulse. And I want to be more elaborate about what I mean by a wave pulse in a moment, but the chat, okay, the chat, hold on a second. Oh, yes, so one person in the chat said, awesome, and then, okay, great, wait, so someone's saying something very important in the chat here too. So someone's saying in the chat, like, it's like clarifying, so a wave is not considered a type of oscillation. Good question. Right, a wave is not a type of oscillation. Let me be a little bit more. Definitely oscillations in general are not waves. You can have an oscillation that's not a wave. Every oscillation that we looked at in the class until all this was not a wave. Like a mass going back and forth on a spring, that's not a wave. Even when we, and this confuses a lot of people, even if we represent a mass going back and forth on a spring with a cosine graph, right? That's a cosine graph. That's not a wave. Like even that picture, that wiggle thing, that's a wiggle. It's not a wave. Why am I saying it's not a wave? Because that is, even if you look at that picture of like up, down, you have cosine. If you look at that picture, it's a cosine in space, but it's not a cosine in time, right? For it to be a wave, that wiggle picture would have to be, it had to be a movie, not just a snapshot, if that makes sense. So oscillations in general are not necessarily waves. Waves can't exist without oscillations. In that sense, your question, direct chat person, like wave is built from the ingredients of oscillations. Oscillation is the crucial ingredient to a wave, which is why we've spent so long studying oscillation, because oscillation is the vital ingredient for a wave. You cannot have a wave without oscillations. But in order to have a wave, you have to have oscillations in time and in space. So at a minimum, a wave is two types of oscillations being put together. Once you put those two oscillations together, then you have a wave. So, I mean, okay, great, okay, cool. Now I'm going to say more. Oh, wait, six. Okay, okay. Yeah, okay.
I have a question.
Yes.
I think I missed it, but what does k equals 2 pi over what?
Oh, over lambda. Sorry, over lambda, where lambda means, sorry. So, okay, I thought you did that line. So that blue thing under the 2 pi is the Greek letter, is the lowercase Greek letter lambda. Sorry. And that's supposed to stand. Okay, sorry. Hold on. That lambda, lambda is used in physics and in science to mean wavelength. So in fact, yeah, I'm going to draw. Well, yeah. So for example, okay, I'll draw it on that. So what we mean by lambda is the length in meters between two peaks of a wave or two troughs, any two of the same, two successive points that are the same in the cycle, that the length of one full cycle from peak to peak or trough to trough or whatever, that's what we mean by lambda, the wavelength, and it's measured in meters. And I'm glad you asked. And what we're saying is, and I'm going to talk about this more in like 5 minutes. What we're saying is, actually, I'm going to say this right now. No, that's a great question. Sorry. I mean, this, of course, this goes on and on forever is the idea. Here, let me. Oh, and there's something else in the chat. I want to dwell on. I think on Remy. I think that was Remy. I hope that was. I think that was Remy.
Yes, that was.
Okay, all right. So I'm going to dwell on Remy's question for a minute, even if, I mean, hopefully I sort of answered it, but I want to say more. I think it's a good, let me say more about it. Let me just see what's in the chat here. Wait, okay. Also, so there's things happening in the chat too. Okay, let me pause for a second. Again, let me just thank you all. I know this is like long, and I think you are a great group. I really mean that. And I mean it in different reasons. I think each of you is making a very different contribution to this whole thing. But it's like, if nothing else, it's really working for me. Okay. Like I really do feel like each one of you in the private chat and in private moments is like really doing a good job of sort of making it clear to me, like what we could do to make this work for you. And I really appreciate that. And I think you guys really are paying attention in lab. It seems like you really are. Why I'm saying nice things, I want to get back to Remy's question, and I also want to move on to the other thing I was going to say. But also, I'm seeing things in the direct chat right now, like that are making clear to me, like, I heard you had a fun time. Maybe that's an exaggeration, but I heard you had a successful, smooth, like unstressful time making the waves out of oscillations, which is great. And again, just for the record, okay, there have been a lot of classes in the past, 102 classes and 204 classes, where forget about comprehension or anything, they had a really stressful time doing that. They found it like really annoying for some. So the mere fact that you guys like had a pleasant time with it already is to your credit. You should know that. Like it's not obvious that that's always a fun day for people. And maybe fun isn't exact, you know what I'm saying? But now let me also say that one of the reasons I'm saying all this stuff, even though to some of you it might feel like it's already clear, is I also know from experience that it's good to feel like things are clear and not confusing. But also sometimes in physics, we feel like things are clear, and that doesn't actually mean that we are actually getting all the points correctly. And I'm seeing some things in chat that are actually indicating me that okay, there may have been some confusion when there might have been certain things that you thought you understood that maybe you didn't when you made the waves out of oscillation. So I think it's important that I'm trying to put this together right now. So keep bearing with me. So on Remy's question, if you look at these two graphs here, this now goes back to lab 3 or whatever it was, the lab before you made waves out of oscillations. If you go back to lab 3, this is very interesting what happened in lab 3. I mean, to me, I think. Here's my understanding. In lab 3, okay, you actually just on purpose made a wave, right? Like we were talking about all these oscillations and everything. You just like stood across from each other and you shook this really long string back and forth until you saw like crests and troughs, like originally going back and forth and then sort of just like going like this and stuff, right? And you took a movie of it. I mean, stop me if I'm at any point wrong, but you took a movie and then like you put the movie into the computers and you put the red dots in and you analyze the red dots, blah, blah, blah. Now, so you're like looking at this whole wave situation and trying to break it down into various equations and stuff. Now, if we step all the way back and think of, and reflect on what you did then, if I'm not mistaken, you made two different graphs. You made two different types of analysis of the same one phenomenon. One analysis you made, I believe, is represented in the top graph here. One analysis is you picked a certain moment in time, call it t equals t naught, right? Like you didn't call it that, but we could call it that. You picked some moment in time. You picked, in other words, some frame from your movie. So some snapshot, right? And you just looked at what your big metal spring looked like in that snapshot, and you put red dots on it, and you made a graph from those red dots. So what your graph was, if you think about it, was treating X as the independent variable. It was treating Y as the dependent variable. It was a graph of like, as you gaze your eyes from left to right on the horizontal axis of your picture, you're asking how high is the metal for any given horizontal spot that you look at, right? You're graphing height of metal as a function of horizontal position. And of course, what you got was like this cosine graph, because at any given moment, the metal just like falls into a cosine shape, right? So the top graph is what you got when you put a bunch of red dots on one frame of your movie. The top graph is what is y as a function of x, assuming that t is a constant. That's what you did for the first graph. You held t constant. You just picked one particular value of time, and you looked at how vertical position varied in response to horizontal position. And you got a cosine graph, like almost not surprisingly, because you're just like looking at a picture of a cosine. Now, note that, so this goes back to someone's question in the direct chat. That itself, that's not a wave. That's a cosine graph. That's all cosine graph in space. It's not a wave. It's a wiggle. I mean, it's just a picture of a curvy snake-like object sitting in space. But then, and it was, and you know it's not a wave because that wasn't your whole phenomenon. That wasn't what you did. That was just a snapshot, a slice in time of what you did. What you did was this wavy thing, right? Now you go to this other graph, or you do this other analysis, where now instead of holding time constant, instead of picking a particular value of t, you pick a particular value of x, like you pick a particular place on the horizontal axis, and you put red dots. You put a red dot wherever the metal intersected, with some reference line at that place, like your ruler or whatever was sitting there. You put a red dot wherever the metal was, and then the frame advanced, right? If I'm not mistaken, if you had the correct configuration in Logger Pro, where it said like you unchecked multiple frames multiple dots per frame or something like that, right? So you put a red dot in, so then the frame advanced. So now the metal's up a little higher on the y-axis. So you put another red dot and then advance the frame. So now the metal's a little higher on the y-axis. You put another dot, So you have this bunch of dots that are just going up and down. Just going up and down now, right? No, I don't see any cosine there. I just see a bunch of red dots going up and down on one line, one vertical line. But you turn that into a graph of y vertical position as a function of time. So this is the bottom graph now. You hold x constant and you look at vertical position as a function of time, and you have a cosine graph again, right? What you were doing in that lab is you were taking a wave and splitting it into the two types of oscillation that were in fact happening at the same time. You were seeing in that lab that what a wave phenomenon is cosines in time at the same time as cosines in space. The distance, back to Remy's question, so first of all, to me, that's like a phenomenal thing. Like we are saying cosines superimposed on cosines is what makes a wave. You have to have a bunch of cosinusoidal oscillators all arranged so that they're staggered cosinusoidally. Right? It's hard enough to make. It's particularly bizarre to think that it just happens automatically ever in nature, but apparently it does. In terms of Remy's question, and I think maybe I already answered it, but if you're looking at y as a function of x, then the space between any two cycles is an x space. It's a space of literal space. It's meters. We call that the length of the wavelength, lambda. But the amount of time between any two cycles, we call period, t. Both of those graphs are independently capturing what a wave is. A wave is really y as a function of x and t simultaneously. But I would need a cube to make a graph of what's happening all at once, right? I would need to really understand a wave. I really need to make a graph of it. I would need height and x and t all in some sort of like mountainous graph. Okay. So what I'm saying so far, what I'm trying to say so far is that in lab 3, you took essentially a wave and you broke it apart to see that actually what the wave must consist of is cosinusoidal harmonic oscillations and cosinusoidal harmonic oscillations in time at the same time as oscillations in space. Then in lab 4, you tried to go backwards and you tried to make the wave from the oscillations. I don't know if you there might be some dispute now whether you actually succeeded or not. I don't know. Or there might have been disputes then of what exactly was going on. But the reason we're doing this so many different ways, like lab, 2 different labs, lecture, this, that, is because at the end of the day, I'm saying we just turned material particles into an immaterial motion. And that's wackadoo. I want to tell you what I mean by an immaterial motion now. Like, so I want to go back to this page where it says, what do we mean? Like I keep saying, oscillations in time plus oscillations in space makes a wave. And I keep yelling like that's a really big deal, because in my heart, I think a wave is a really big deal, but you may not yet. I mean, maybe you're so used to waves that you're not necessarily sure why I think they're so interesting. Here's why I think they're so interesting. And why they're like actually the point of this course. When I say that there's wave, it's not clear. Hold on. What do I mean by wave motion from here to there? When I say here and there, picture, for example, one lab partner and another lab partner, okay? When I say that a wave travels along the long metal string from one, like, so picture your 2 lab partners, okay? And picture, don't worry about all the graphing and all the details of that whole experiment. Just imagine you're one lab partner standing over here and there's another lab partner over there, and you take your end of this long metal spring and you flick it, just like once, okay? We're just gonna talk about like one wave pulse. You flick it, and you see this ripple, or stop me if this doesn't make sense, but I think if you like flick your end just like once, you'll see this bump or this ripple, this crest, this, I don't know what else to call it, this bump, this distortion, this shape in the wave travel from you to your lab partner, right? You see it with your eyes, and it's not a misperception. It's not an illusion. You could be like, for example, you could say to your, well, first of all, wait, before I go any further, is everybody with me so far? Like if you flick one end of the, can you picture flicking one end of the metal spring and just like seeing that bump that travels across to your partner? Do you know what I'm talking about with that? Can you just like signal me if you, okay, thank you. That's good. Okay, I'll take it. Okay. So I really want you to consider this for me, like have it in your mind. I know you've seen it a million times and you've seen it in water ripples and you've seen, but I really want you to think about this now, what's happening when, oh, cool. Thank you both. I'm not going to try to confuse you. I'm going to try to ask you to appreciate something very bizarre that's going on. When you flick that metal and the bump, the disturbance, the distortion, the crest, the peak travels from you to your partner. First of all, it's not a misperception. Like it is happening. I mean, you could even make an arrangement with your partner in advance. You could be like, okay, the minute the bump gets to you, I want you to ring a bell, or I want you to make a sound, or I want you to start a stopwatch or something, right? And you could make that arrangement with a third party. Like you could all agree, like, I'm going to send a wave pulse to you. And when it gets to you, like the experiment's over or something like that, right? And everybody will know what you're talking about. You're not going to all agree perfectly exactly when the bump gets to your other lab partner, but you're going to agree to the same extent that if you decided to throw a baseball to your partner and say, as soon as you catch the baseball, we're going to start a stopwatch or we're going to make a sound or something, like you would have the same level of agreement and recognition and clarity sending this bump to your partner as throwing a baseball to them, I would say. But let me go a step further. So you send this bump to your partner And after you do that, you could measure the distance between you and your partner, right? And you could measure the amount of time, like you could agree, all right, as soon as I go like this, I'm going to start my stopwatch. And as soon as the bump gets to you, you're going to stop your stopwatch. So we're going to find out at the end how much distance this thing traveled. And we're going to find out how much time it took. So we're going to divide one by the other. We're going to get a speed, right? And which you talked about in the board meeting yesterday, 2 days ago. We're going to get a speed. And with that speed, we can now make predictions. We can say like, oh, the thing traveled 3 meters per second. So therefore, if we let it travel for 3 more meters, it'll probably take another second, or right? And I'm not saying any of your calculations, or I'm not saying any of your predictions will be perfect, but I'm saying they'll be just as reasonable as they would be for a baseball. In other words, what I'm saying so far, of course, I will write this down in a minute, but what I'm arguing so far is that when you send a bump to your partner, when you send a crest or a disturbance to your partner, there is a motion that is as observable, as measurable, as calculatable, analyzable, and as predictable as any other motion in physics, in space and time, right? Like when that bump travels from you to your partner, it is a real motion. It is totally scientific motion. It is subject to reproducing it, to measuring it, to putting it into our typical physics equations and spitting out answers and then predicting its future trajectory. And we'll be right about all that stuff. We will be as right as we ever are about baseballs or planets or cannonballs or whatnot, right? So far what I'm arguing is when a wave pulse travels from here to there, what I'm arguing so far is okay. So, oh wait, something in the chat. Hold on. Oh, okay, cool. Okay. So far I'm saying hopefully the obvious. I don't think that anything I'm saying so far is like mind-blowing. I'm just trying to set a stage for the thing I'm saying but I do want to establish this. When you send your bump from you to your partner, that bump is a motion that we can observe, measure, analyze, and predict. It's a totally scientifically verifiable and meaningful motion that occurs, right? And there's no big mystery, like what's moving? Metal, right? Like there's stuff that's doing the motion. Like in this case, in the case of the lab, it's pieces of metal that are moving and motion is occurring from you to your partner. But the big but, it's such a big but, the big but is this. The key point here, I'll read my words out in a minute. Well, I'm saying wave motion from here to there means motion occurred from here to there. That passes every test of science I can imagine. But no individual thing at all moved from here to there. To be more specific, I'm saying when you do it on a long string of metal, a motion occurred from you to your lab partner. And there was a bunch of metal moving. And the only thing that was moving was a bunch of metal. But no piece of metal ever made a journey from you to your partner. It's that simple, but it's that crazy. I mean, and again, it's so simple that it might seem stupid that I'm bothering to say it, but actually it's not at all stupid. It's crazy. We're seeing something move from me to you. We're measuring something move from me to you. We're reproducing something move from me to you. We're predicting how fast it's going to move from me to you. But there's no thing moving from me to you. Like literally, there is no thing moving from me to you. There is something, but there's no thing. Well, how can I say it? I'm saying a wave is something moving where there's nothing moving. What do I mean? Again, what I mean is there's metal making a motion, but there's no metal undergoing the motion itself. The motion is from me to you. The motion is, in this case, horizontal. But the only motion that's happening is happening of metal. The only thing moving is metal, and you cannot find a single piece of metal that's moving horizontally. Like what? Like really, that means that we have put a bunch of metal, in the case of metal, I mean, it could be anything that we're talking about, but this whole idea is that we put a bunch of little objects, we've set them up to oscillate in their little neighborhood, and we've set up their oscillations. So we've set up each object to have an alternating kind of motion. And then we're alternating the alternations just so that at the end of the day, a bunch of things that are vertically moving create a horizontal motion. There's no material entity making that horizontal journey, but the horizontal journey does occur. I am saying when a wave pulse travels from here to there, no particle travels from here to there. No material object travels from here to there. A wave pulse is immaterial motion. Scientists are here to study the material world. We are here to study stuff moving through space and time. But here we have a motion through space and time that isn't stuff, and yet it's totally real. It's totally real. I think that's a very, very big deal. Honestly, like it's actually what this course is about. What we're actually studying is in Physics 101, what you studied was the trajectories of particles, the journeys that objects make, such as baseballs. And when a baseball or a cannonball or a planet, or even an electron for that matter, when an object makes a journey from here to there, it actually goes from here to there. And you can slow down the movie and say, first it was here, then it was here plus one, then it was here plus two, then it was here plus three, then here plus four, and then it was there. Now we're studying, I'm going to write this down. Hold on a second. Hold on. So I'm saying in Physics 101, you study the trajectory of particles. Here, we're studying motion still, motion through time and space, but it's not the motion of particles anymore. As of this moment now on, we took a bunch of particles and we put them together in a kind of a way to create this motion, or nature put a bunch of particles together and set them in these set them up in a pattern of patterned motions, right? Like again, we're alternating a bunch of alternating motions so that what ends up happening is a new kind of motion that itself is not material. A wave pulse is not the trajectory of a particle, it's the propagation, which means immaterial motion. It's the propagation of, well, you could call it of energy if you like. It's not of particle, it's not of matter anymore. You could say that a wave pulse is the propagation of energy. What I like to say is it's the propagation of information. Like what's here, actually. What you're sending when you send a wave pulse from you to your lab partner, you're not sending a thing to them. I mean, you're not sending a thing to them. You're not sending a particle. You're not sending an object, but you're sending something. What are you sending? I would say you're sending information. You're sending like data. You're sending an ability or a capacity or a disturbance. One way to put it. We're actually almost, so I'm saying what a wave pulse is, it's not a thing, right? I keep saying that because it's like really exciting to me. Like, I don't know, to me, and this is like in a weird way why all the math gets abstract and all this, because we're finally at a point in physics where what we're using our techniques of studying the material world to actually start studying immaterial phenomena in the material world. Like when I started doing physics, I didn't know that was like part of it. I didn't know I was going to be studying stuff that I could not touch, see, feel, hear, or smell. I mean, I don't know if you know what I mean by that, but like a wave is not a tangible thing, but it is a motion through space and time, and it is real. What is it? It's a disturbance in a medium. A medium is that bunch of particles that allows this to happen in the first place. Like in the case of your metal spring, like metal is the medium. Or in the case of, say, sound, right? The medium generally is air. When I'm talking to you, forget about the internet and all that. Forget that, like, there's also, like, forget the internet. Let's say we were in the same room, say we were in office hours right now, and I was talking to you right now. Like, I'm sending sound from my mouth to your ear, right? I think most of you have some awareness that that sound that is going from my mouth to your ear, we call sound waves. We regard it as a wave. What does that mean? It means, and you may have even heard when you were little, like if I were in outer space right now where there's no air at all, and if say there was no water and no air and nothing, if I were in outer space, you wouldn't hear me at all, right? Like you may have heard that, and that's true. That's not a myth. I mean, sound does not travel in outer space. Why? Because sound is not a thing. I mean, things can travel in outer space. Rocks can travel through outer space. Meteors travel through outer space. The reason sound cannot travel through outer space is because sound doesn't exist on its own. When I talk to you in my office hours or something, there's air between us. And what we're believing is a little bit of air molecules over here oscillate harmonically, and then a bunch of air molecules over here oscillate harmonically, and then a bunch over here, just like we've been saying, for 2 hours today. It happens that with the air molecules, to be fair, with the air molecules, it's not that they go up, down, up, down, up, down. They actually go side to side, side to side, side to side, but it's the same point, and it's the same math and everything. In that, when I talk to you, air oscillates, air oscillates, air oscillates, air oscillates, and it finally gets to your eardrum and you hear it. The only thing that's moving is air. If you took away the air, you wouldn't hear me at all. But there's no individual particle of air that's going from my mouth to your ear, I hope. Like that would be gross. When I talk, I'm not sending an air molecule to your ear. I'm sending a ripple through the air molecules to your ear. I'm sending a ripple. What is a ripple? It's this. It's a disturbance in the medium. It's just like a crest and then a trough. The air was originally just organized all flat, just like all hanging out between me and you. And then like I disturbed it. I vibrated the air over here, and then I vibrated the air over there, and then vibrated over there. What I'm sending to you is a disturbance in the medium. A disturbance is not a thing. I'm just messing with the thing. The thing is called the medium. The thing is the vast collection of oscillators that are dancing in such a particular way that what they end up doing is sending information from me to you, whether it's through metal shaking up and down or air vibrating or ripples in water or whatever. A wave is an immaterial disturbance in a material medium. It's kind of, and it's what's amazing is that they happen at all, let alone that once they start happening like sound waves, they happen in all these particular recognizable frequencies and wavelengths and amplitudes, such that at the end of the day, we can recognize like a middle A on a piano, middle C, or music, or my language. Like all of this stuff is waves, and all of them are real, but none of them are real things. Ultimately, I'm saying a wave is a collection of phase-staggered oscillators. That is ultimately what I'm saying. And that's what you have been showing the last couple of days. And so now we're just about done. To bring this back full, so all the math and all the work that you've been doing to understand oscillation has all been trying to get us to this point. We need to understand oscillation so we can understand. So we need to understand that y equals a cosine omega t equation, so we can understand that a wave is y equals omega cosine. Y equals a cosine omega t plus or minus kx. A wave is the cosines happening in time while it happens in space. A wave is an immaterial thing that is brought about by a bunch of material things behaving in a very intricate fashion. Sorry. Wait, sorry. Yes, absolutely. Yes. Okay. I'm going to say good point in the direct chat. Yes. I forget how much I've said about that in my office. Yes. 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 And I'm getting there. But I also, I know I'm having a private conversation right now. Hold on a second. Okay. Hold that thought for a second. And we're almost done with class 2. I understand that. And you've been very good, all of you. I wish I could give you a cookie. wait, a quick, and I am watching the time, I promise I won't let you go late, that's for sure. Quick question though, in this class, I'm pretty sure, I'm just gonna make sure, on the very first day, we did that thingy thing, unthingy thing, like thought experiment with the two objects on the table, right? Or did we do the thingy thing versus unthingy thing on the first day in
It
this
was
class?
homework 1A.
Right, okay. But we talked about it briefly in class, or you just did it and I never, okay. 1A, right, okay, good. So I wanted to circle back to that. Thank you for all this participation. You guys have been great. I don't know why I keep saying, but it's true. So I want to bring this back to that for a minute. And I want to address one thing that I just saw in the direct chat, and hopefully then I'll be able to, and you didn't have a break or anything. So hopefully I'll let you go in a couple, I can't promise, but hopefully in a couple of minutes, but certainly before 7:10. Just to remind you, like when I say a wave is not a thing or is not a thingy thing, going back to that first day, remember what, like I'm trying to argue that there's all kinds of things that travel through space and time that are the province of science, particularly physics, right? But not all things are thingy things, right? And what makes something a thingy thing, what makes it a particle in proper scientific terms, to be a particle is to be something that cannot be in two. A particle is something that cannot occupy two space points at one time point, nor can it co-occupy one space point at one time point with another particle. Let me put that in English. What it means to be a thingy thing is you can't be in two places at once, and you can't be at the same place at the same time as another particle, right? That's what makes these material is they can't be in the same place at the same time. And also one of them cannot be over here while it's over there. But a wave totally can violate both of those things. And you know that anytime anybody, I think we said this on the first day, but if you've ever heard two sounds at once, if anybody ever talked at the same time I was talking and you heard it, or if you've ever heard any song ever of music, like if you ever heard two notes at once, i.e. a chord, or you ever heard someone singing while they play the guitar, whatever, if two sounds are literally hitting your eardrum at the same time, that ain't no accident, and that's not a contradiction. That's something sound. Or if you've ever worked in the theater, and now to bring this to the direct chat person thing, if you've ever worked in the theater and you've shown a red spotlight on a spot and shined a blue spotlight on the spot, the blue spotlight doesn't knock the red spotlight out of the way, right? The red and the blue can occupy the same place at the same time as though they were ghosts. It's not, but they're not ghosts. They exist, and they exist in space and time. But they're not objects. They're information propagations, and information propagations can share space. It's called interference, constructive or destructive. And also, if you were thinking about, okay, what about the other thing? Like how a light can be in two places at once. Can a light or a sound be in two places at once? Let me put it this way. Can it not? Can a sound ever only be in one place? I would argue no. I'm not just arguing, I would assert no. Like sound intrinsically is a wave. Wave intrinsically is a type of motion. A wave is always in motion. The minute it stops, it's not a wave anymore. And you don't have sound anymore. For sound to be sound, it can't only be in one place at one time. It wouldn't be sound then. And let me remind you again, sound. So now I'm going to finish by responding to something in the direct chat, and that'll be good enough for today, I hope. Like, remember, okay, so someone's saying something in the direct chat about that this becomes even more interesting when you consider like the question that some of you may have heard of whether light is a particle or a wave. Now that is the most interesting thing to consider for sure. And that is the punchline of this whole class. I'm not trying to hide the ball or do a spoiler alert or whatever. The whole punchline of this whole class, the whole ultimate thing we want to look at is light. And that's we're building toward there step by step, motion by motion. But let me say, it doesn't have to be light for this to be an interesting question. When people ask, is light a wave or a particle? What I'm here to tell you right now, like I'll tell you, I heard that question for years when I was in high school and particularly college. I heard over and over again in science class after science class, people didn't know, is light a wave or is light a particle? Is light a wave or is light a particle? First, this genius thought this and proved it beyond a shadow of a doubt. And then 300 years later, this other genius proved that the first genius was a retard, was an idiot, and like proved the opposite beyond a shadow of a doubt. And then 100 years later, this genius proved that the other two geniuses were clowns and proved it beyond a shadow of a doubt. And then we got to the 20th century. I don't know if you've heard this before, but I heard this all the time in college. And don't forget, I signed up to be a physics major. And I was here. Thank you. Okay. And I was hearing this all the time. And it was driving me crazy, especially, and I'm watching the time, especially when all these classes, they finally got to the point where they're like, after hundreds and hundreds of years of geniuses going back and forth and throwing egg in each other's face, then we got to the 20th century where the real geniuses live, like us. We got to it was the 20th century when I was in, when we got to the 20th century and the real geniuses stepped forth and said, here's the real genius answer to whether light is a wave or a particle. We say it's both. Doesn't that blow your freaking mind? And I was like, no. And remember, I wanted to be a physics major, but I was like, are you kidding me? That is the stupidest waste of my time I could possibly imagine. You're literally telling me that for centuries, geniuses went back and forth going, is this ice cream vanilla or is it chocolate? I think it's vanilla. I prove it's chocolate. I prove it's vanilla. And it took a 20th century bunch of big old geniuses to go, actually, it's a swirl. We never thought of that before. I'm like, really? It couldn't have just been a swirl the whole time? Like, no one thought of that? And furthermore, like, why is that so, like, it's a swirl, fine, it's a swirl. But here's the thing, and I know I've got 5 minutes left. What I'm trying to tell you is, no, they actually did it. They didn't explain it well to me, I don't think, but they actually had a point. What they were, see, if you just say is light a wave or a particle, if you say is anything a wave or a particle, it sounds like you're just saying which flavor is it? And of course, it could be both flavors. But what I'm really here to try to tell you that I did not understand for decades. What I'm here to tell you is that to ask if something is a wave or a particle is not to ask what flavor or type of thing it is. It's to ask, is it a thing at all or not? Like with sound, the deal is when we say that sound is a wave, what we're saying is sound doesn't exist. There's not a thing called sound. Sound is a disturbance in a thing called air. We're saying when we say that sound is a wave, we are saying no matter how powerful your microscope is, no matter how advanced your technology is, you will never find a little grain of sound. There is no such thing as an item or a bit or a countable, separatable element of sound. When we say that sound when we say sound travels as a wave, we're saying there's no existing, there is no sound. There is just a very complicated disturbance of air. Air is the thing, the noun, sound is the verb or the activity that air is undergoing. First of all, that is fascinating to me, to find out that there's no such thing as sound. There's just an activity that a bunch of things are performing that give rise to the effect of sound. I think that's interesting. But then second of all, and I'll end on this because I know the time, but the person who asked in the direct chat, like, so then though, for centuries, when people were trying to study whether light was a particle or a wave, what they're really trying to study is, does light exist or not? They couldn't tell whether there were little bits of light, like there are bits of wood in the world, or not. Like there are bits of wood exists. There are not bits of sound. Sound doesn't exist. It is a clear dichotomy, and you can't exist and not exist at the same time. So when they were asking, is light a wave or a particle, they were really asking, is there such thing as light or not? And for anybody in the 20th century to say it's both is completely insane. Like that's literally saying we believe this thing exists and yet it doesn't. What? So that is where this whole course is heading. We're not going to do all that right now, but I want you to appreciate that now that we're talking about waves, finally, a wave is a type of motion. It is not a type of thing. To move as a wave is to not be a thing. That's what we're saying. And where does it come from? It comes from a bunch of things doing something very intricate and very cosinusoidal called harmonic oscillation. Okay. Oh, that's so cool. Okay. Well, thank you for what's in the chat. Okay. Okay. So that's it. That's today. I mean, well, that's so great. Okay. So hopefully that made some sense. We'll keep doing this next week. Blah. Wait, we have class next week and then we break. Okay. So I'll hang out for a second if there's any questions or complaints or anything. But have a great. There's no more homework. Just don't worry about homework right now. If you do owe me anything, to give it to me. That's all. Okay. Goodbye. Have a good night. Oh, I thought it was late. Have a good night. Have a good night. Oh, thank you. No, great job. Thank you. Yes, have a great, yes, okay, yes, thank you.
Hello, Professor.
Yes, hi, wait, let me stop the recording. One second.